Alright, let's go. Number 12. The heartbeat that was almost mistaken for aliens. In November 1967, a 24-year-old graduate student named Jocelyn Bell Burnell was reviewing kilometers of chart paper at the Mullard Radio Astronomy Observatory in Cambridge, working under her supervisor Anthony Hewish, when she noticed a strange, impossibly regular pulse of radio energy repeating every 1.3373 seconds. It was more precise than anything believed to occur naturally in deep space, more regular than any known pulsar, quasar, or variable star cataloged at the time. For weeks, the research team half-jokingly labeled the signal LGM-1 for Little Green Men, genuinely entertaining the possibility they had detected an artificial beacon from an alien civilization. Bell Burnell later recalled the strange tension of those weeks, torn between scientific excitement and the fear that she had accidentally found proof of intelligent life using a radio telescope built from scrap wire and wooden posts. What the team eventually discovered was a rapidly rotating neutron star, a pulsar, sweeping a narrow beam of electromagnetic radiation across the Earth with every single rotation, like a cosmic lighthouse built by nature rather than by any intelligence. The 1974 Nobel Prize in Physics was awarded for the discovery, but controversially, it went to Hewish alone, a decision the scientific community still actively debates today, given that it was Bell Burnell who first identified the anomaly buried inside the data. What makes this discovery unsettling in hindsight is not just the controversy over credit, it is how close human science came to mistaking a natural stellar corpse for an intentional transmission, and how a signal that mechanically perfect, ticking with the regularity of an atomic clock, could exist anywhere in the natural universe without a mind behind it at all. Since that discovery, astronomers have cataloged more than 3,000 pulsars across the Milky Way, each one a spinning neutron star broadcasting its existence into the void, and every single one of them began as a collapsing, dying star. Number 11. A sugar cube of it would weigh 1 billion tons. Neutron star matter is not simply dense. It is a form of matter that, under any conditions found on Earth, should not be able to exist at all. When a massive star, at least 8 times the mass of our Sun, exhausts its nuclear fuel and collapses under its own gravity, its protons and electrons are crushed together with such catastrophic force that they merge into neutrons, compressing an entire star's worth of mass into a sphere roughly the width of a city like London or Chicago, typically between 10 and 12 miles in radius. The resulting density has been calculated at approximately 3.7 times 10 to the 17th kilograms per cubic meter, roughly comparable to compressing the entire population of Earth's oceans into the volume of a single grape. A single sugar cube of that material, about 1 cubic centimeter, would weigh close to 1 billion tons on Earth's surface, comparable to compressing the entire mass of Mount Everest into a space smaller than your fist. To put that in perspective, if you could somehow transport a teaspoon of neutron star material to Earth, the sheer weight would punch through the crust of the planet and continue falling toward the core, essentially unstoppable by any structure humans could build. No laboratory on the planet can replicate this density. No particle accelerator, not even the Large Hadron Collider at CERN, which can recreate conditions similar to the early universe for fractions of a second, has come remotely close to sustaining matter at this density for any meaningful length of time. Physicists study this material entirely through gravitational mathematics and light, gathered from thousands of light years away, calculating the behavior of matter more extreme than anything humanity will ever be capable of physically producing, holding, or testing directly in any facility on Earth. Number 10. It has mountains, and they're barely taller than a fingernail, and they might still be warping the fabric of spacetime. Because a neutron star's surface gravity is roughly 200 billion times stronger than Earth's, its crust is almost unimaginably smooth, smoother in relative terms than a billiard ball. Researchers Fabian Gittens and Nils Anderson at the University of Southampton calculated in research published through the 2020 S that the tallest possible mountain a neutron star's crust could sustain, a deformation supported by the extraordinary tensile strength of its crystallized outer layer, made of a lattice of atomic nuclei locked under immense pressure, could be no taller than a few millimeters before the crust itself would simply fracture under the star's own gravitational weight. Earlier estimates in the early 2000s had suggested mountains up to several centimeters tall, but more refined models of crustal breaking strain have repeatedly revised that number downward. And yet, according to general relativity, even a mountain that small, sitting on an object rotating hundreds of times per second, is theorized to be massive enough to generate continuous gravitational waves, persistent ripples in the fabric of spacetime, detectable in principle by observatories like LIGO and Virgo. As of 2026, no such continuous wave wave signal has been confirmed from any known pulsar, despite years of targeted searches by LIGO scientific collaboration teams pointed specifically at nearby rotating neutron stars like the Crab pulsar, which means physicists are currently searching for space-time distortions caused by bumps smaller than your thumbnail, sitting on objects trillions of miles away, spinning faster than a kitchen blender, and they have every theoretical reason to believe those distortions are really there, quietly rippling outward across the galaxy, undetected. Number 9. A single starquake in 2004 briefly disturbed Earth's own atmosphere from 50,000 light-years away. On December 27, 2004, satellites orbiting Earth, including NASA's RESI spacecraft, detected an event so powerful that for a fraction of a second, it saturated nearly every gamma-ray detector in orbit and measurably ionized the upper layer of Earth's ionosphere, an effect normally caused only by solar flares originating from our own sun. The source was a Magnetar designated SGR 1806-20, located roughly 50,000 light-years away, almost on the opposite side of the galaxy from our solar system. In approximately 1/10 of a second, this single starquake, a violent fracturing of the neutron star's rigid crystallized crust, released more energy than the sun produces in 100,000 years combined. Researchers, including work published by Brian Gainsler and collaborators in the journal Nature, have estimated that had an equivalent event occurred within 10 light-years of Earth, it could have triggered a genuine mass extinction event, stripping away significant portions of our atmosphere's protective ozone layer within moments. Some researchers have even speculated that a Magnetar starquake at close range in Earth's ancient past could explain certain unexplained extinction events in the geological record, though this remains entirely unconfirmed and highly speculative. This was not a supernova. It was not an explosion in the traditional sense. It was simply a crack forming in the surface of an already dead star, a stellar corpse fracturing like an eggshell, and it was powerful enough to physically reach across the galaxy and touch our planet from a distance almost incomprehensible in scale. Number 8. Its magnetic field is strong enough to rearrange your body's atoms from 1,000 kilometers away. In 1992, physicists Robert Duncan and Christopher Thompson, then at the University of Texas at Austin, theorized a distinct subclass of neutron star they called a magnetar, an object possessing a magnetic field up to a quadrillion times stronger than the magnetic field generated by planet Earth. That number is difficult to make meaningful, so consider this instead. Physicists have calculated that if a magnetar existed within roughly 1,000 kilometers of our planet, a distance shorter than the flight from New York to Chicago, its magnetic field would be strong enough to physically disrupt the electron clouds surrounding the atoms in the human body, unraveling molecular structure itself before any other effect could occur, effectively erasing the chemistry that makes biological life function. It would also instantaneously erase every piece of magnetic storage media on the planet, every hard drive, every credit card strip, every server farm on Earth, from that same range. Some magnetars have been observed to release enormous bursts of energy called giant flares, and the 2004 event from SGR 1806-20 mentioned earlier was, in fact, produced by exactly this kind of object. Roughly 24 confirmed magnetars currently exist in catalogs maintained by astronomers around the world. All of them, mercifully, sit thousands of light-years from our solar system, and astronomers monitoring the galaxy intend to keep it that way in every long-term model they run. Number 7. Beneath its solid crust, it may contain a superfluid that has never once stopped moving since the day it was born. Observations of the neutron star sitting at the center of the Cassiopeia, a supernova remnant roughly 11,000 light-years away, published in 2011 by researchers Danny Page and Win Ho, revealed that the star was cooling far faster than existing theoretical models predicted, a rate of temperature decline that puzzled the astrophysics community upon release. This unexpected cooling rate is consistent with the interior neutrons undergoing a phase transition into a superfluid state, a form of matter with effectively zero viscosity that, once set into motion, would continue flowing forever without ever losing energy to friction, a phenomenon otherwise only observed in laboratory conditions cooled to near absolute zero using liquid helium. This suggests a neutron star may possess a rigid crystalline outer crust made of ordered atomic nuclei locked into a lattice structure, wrapped entirely around an interior ocean of frictionless superfluid neutrons that has been swirling, undisturbed and unceasing since the exact moment the star was born in a supernova collapse, potentially for tens of thousands of years without a single moment of interruption. Two entirely different phases of matter, one frozen absolutely solid, capable of fracturing like glass during a starquake, the other flowing in perpetual frictionless motion, coexisting simultaneously inside a single object smaller than most major cities on Earth. Number 6. It sometimes suddenly speeds up its own rotation for no external reason anyone has ever directly observed. Pulsars are known throughout astrophysics for extraordinary rotational precision, timekeeping so exact that some millisecond pulsars rival the stability of atomic clocks used to define international time standards. But occasionally, without any external trigger or warning, they suddenly and abruptly spin faster. The phenomenon, first documented in the Vela pulsar in 1969 by Australian astronomers Venkataraman Radhakrishnan and Richard Manchester, is formally called a glitch. The leading theoretical explanation is that the superfluid interior of the star rotates at a slightly different speed than its rigid outer crust, and periodically, vortices circulating within that internal superfluid suddenly unpin from the crust and transfer their angular momentum outward all at once, kicking the entire star's rotational speed upward within a fraction of a second, a shift so small it can only be measured through the precise timing of the pulsar's radio beam, yet undeniably real. It is in effect a neutron star briefly and involuntarily shrugging its own shoulders. The Crab pulsar, born from a supernova observed by Chinese astronomers in the year 1054, has glitched repeatedly since its discovery in 1968, and physicists still cannot reliably predict exactly when the next glitch will strike, on the Vela pulsar, on the Crab pulsar, or on any of the roughly 3,000 pulsars now catalogued across the galaxy. Each glitch offers a rare glimpse into a physical process happening inside a star that no human instrument could ever directly access. Number 5. There is a mass limit beyond which a neutron star simply cannot exist, and we still don't know its precise value. In 1939, physicists Robert Oppenheimer and George Volkoff, working together at the University of California, Berkeley, published a landmark paper in the journal Physical Review, calculating the maximum possible mass a neutron star could sustain before its own gravity would overwhelm even the immense outward pressure of degenerate neutron matter, forcing further collapse, potentially into a black hole from which nothing, not even light, could ever escape. Their original estimate was crude by modern standards, roughly 0.7 solar masses, far below what we now know neutron stars can actually reach. But the underlying concept, now formally called the Tolman-Oppenheimer-Volkoff limit, remains one of the most intensely studied numbers in all of theoretical astrophysics. Modern calculations, incorporating decades of refinement in nuclear physics, place the limit somewhere between 2.2 and 2.9 solar masses, and in 2021, the Nanograv collaboration confirmed a neutron star designated PSR J0740 plus 6,620, with a measured mass of approximately 2.08 solar masses, pushing dangerously close to the theoretical boundary of what matter can survive without collapsing further. Physicists still do not know the exact number at which a neutron star exhausts the last defenses of known physics and collapses into something else entirely, a black hole, or potentially something even stranger that current theory has not yet named. We only know that boundary exists somewhere out there, silently waiting to be crossed by the next star that tries to exceed it. Number 4. When two of them collide, they forge the gold currently sitting in your jewelry box. On August 17, 2017, the LIGO and Virgo gravitational wave observatories detected a signal designated GW170817, produced by the collision of two neutron stars located roughly 130 million light-years from Earth, in a galaxy called NGC 4993. For the first time in the history of astronomy, the event was also observed simultaneously across the entire electromagnetic spectrum, from gamma rays to radio waves, by roughly 70 observatories around the world working in coordination, confirming a long-standing theoretical prediction. Neutron star collisions produce what is called a kilonova, an explosion violent enough to fuse atomic nuclei together through an extremely rapid process of neutron capture known as the R process, generating heavy elements that ordinary stellar fusion inside stars like our Sun can never produce on its own, no matter how long that star burns. Gold, platinum, Uranium. Every heavy metal atom on Earth heavier than iron most likely originated in an event exactly like this one. Two collapsed stellar corpses smashing into each other with such unimaginable violence that the resulting wreckage became precious metal, flung outward into space to eventually seed future solar systems, including our own. Scientists estimate the 2017 collision alone produced heavy elements equivalent to several times the mass of the Earth. The gold sitting in your jewelry box or wrapped around your finger right now is very likely older than our entire solar system, and it was forged in the violent death spiral of two neutron stars colliding somewhere in deep space, long before our sun ever ignited. Number 3. Some of them might not actually be made of neutrons at all. In 1984, physicist Edward Witten at Princeton University proposed in a paper published in Physical Review D that under sufficiently extreme pressure, neutrons themselves could theoretically break down even further, dissolving into a deconfined soup of up, down, and strange quarks, forming an exotic state called strange quark matter, which Witten argued could actually be more stable than ordinary nuclear matter under the right conditions, a hypothesis now known as the Bodmer-Witten conjecture. If this theory is correct, then some objects currently classified as ordinary neutron stars might actually be an entirely different kind of object called a quark star, composed of a phase of matter that has never once been directly observed anywhere else in the universe, and that cannot currently be replicated or verified in any Earth-based laboratory. In 2022, researchers analyzing the neutron star sitting at the center of supernova remnant Hess J1731347, published in the journal Nature Astronomy, found it to be unusually light and unusually small for its classification, a combination some physicists argued was more consistent with a quark star than a conventional neutron star, potentially the first observational candidate of its kind. The result remains actively disputed within the astrophysics community, with several competing groups offering alternative explanations involving unusual crustal compositions. But it raises a genuinely uncomfortable possibility that some of the objects astronomers have confidently been calling neutron stars for over 50 years may not be made of neutrons at all, but of something with no established name, no laboratory precedent, and no known equivalent anywhere else in nature. Number 2. Standing on its surface, you could theoretically see the back of your own head. The gravitational field at a neutron star's surface is so extreme that it visibly bends the path of light traveling across it, an effect known as gravitational lensing, predicted directly by Einstein's general theory of relativity. Physicists have calculated that this curvature is severe enough that light emitted from the far side of the star can bend entirely around its own surface and become visible to an observer positioned facing it, meaning a hypothetical viewer standing on the surface could in principle see more than half of the entire star's surface area at once, with light wrapping around the sphere and arriving simultaneously from multiple directions, distorting the visual geometry of the object into something the human brain has no framework to properly interpret. Time itself would also behave differently in that environment. Clocks positioned at the surface would run measurably slower than identical clocks in orbit above, a direct and unavoidable consequence of gravitational time dilation, operating at nearly its most extreme observable limit anywhere in the universe outside of a black hole's event horizon itself. A signal broadcast from the surface, if such a thing were survivable, would arrive to an outside observer measurably delayed and redshifted, stretched by the sheer curvature of spacetime surrounding the star, a direct, physical demonstration of relativity operating at a scale no human has ever experienced firsthand. Number 1. Nobody actually knows what is sitting at the very center. Every single observation, every equation, and every model discussed throughout this entire list ultimately depends on one unresolved variable that physicists call the equation of state, the precise mathematical relationship between pressure and density inside a neutron star's innermost core. At the surface and outer layers, physicists understand the behavior reasonably well, confirmed through decades of nuclear physics experiments. But deep in the core, where densities may exceed even the extreme values found in the outer layers by a significant additional factor, potentially several times the density of an atomic nucleus itself, the behavior of matter becomes genuinely unknown territory, a region physicists sometimes refer to, only half-jokingly, as terra incognita. Leading theoretical models propose the innermost core may contain hyperons, exotic particles containing strange quarks not found in ordinary matter, or a fully deconfined quark-gluon plasma, similar to conditions that existed microseconds after the Big Bang, or even a theorized phase called color superconductivity, in which quarks pair together in a manner mathematically analogous to superconducting electrons in a laboratory on Earth. Since 2017, NASA's NICER mission, the Neutron Star Interior Composition Explorer, mounted directly on the International Space Station under the direction of researchers Zayvon Arzoumanian and Keith Gendreau, has been measuring neutron star sizes and masses with extraordinary precision, attempting to finally determine which of these competing models is correct by mapping hotspots on pulsar surfaces with unprecedented accuracy. As of 2026, the true nature of the matter sitting at a neutron star's core remains one of the largest unsolved problems in all of modern physics, a question that sits at the intersection of general relativity, quantum chromodynamics, and nuclear physics, three fields that rarely have to speak directly to one another anywhere else in science. Somewhere in our galaxy right now, packed inside objects smaller than most cities, there exists a phase of matter unlike anything found on Earth, unlike anything ever created inside a laboratory, and unlike anything current physics can fully or confidently describe, and it has been sitting there in total silence for millions of years, spinning, cooling, occasionally cracking, waiting for an instrument sensitive enough to finally tell us what it actually is. If you want to see more videos like this, click the video on screen now, and make sure to subscribe.